Thank you very much. It's a pleasure to be here. I want to thank the organizers, in particular Roland, for the kind introduction and for taking care of all the logistics. Okay, as mentioned, today I want to talk about deep neural networks and some recent work that I've been doing with some of my graduate students on understanding implicit and explicit regularization in deep networks and what that means for further performance, particular generalization. Let's see here. Oh, there we go. Okay, so a few words, I don't know if I need to say a whole lot about deep learning. I mean, as we all know, it's kind of changed the landscape of machine learning the last, several years. It's enjoyed a great deal of success in a wide variety of applications, speech recognition, all kinds of computer vision, all kinds of things. So much so that students, come and take machine learning classes, and basically what they want to know is what button on TensorFlow do I have to press? That's kind of the status, as someone like myself who's a bit of an outsider, this is surprising because, at least from afar, when I look at it, there haven't been a whole lot of new ideas compared to the 90s, which was another era where neural networks were popular, not to this extent, but nonetheless. And so there's a lot of natural questions that might come up. Why is it that, deep learning has enjoyed this success? Multi-layered neural networks were in vogue in the 80s and 90s as well. And so there's discussions, perhaps it's, the network architecture that makes the difference. We have convolutional networks, they're highly over-parametrized, there's, multiple layers. We've moved from sigmoidal nonlinearities to ReLU type nonlinearities and so on. People might say, well, it's just because, we're in the era of big data, we have much larger data sets, much more computational power, and that's where, the strength of deep learning has manifested itself. And others might ask, maybe it's the algorithms or something that's happened here. And so I kind of view, this is akin to the parable of, the blind man and the elephant. Everyone is touching a, particular part of the elephant and thinks that, that's what it is. And so probably understanding what's going on with deep learning is really, one has to look at it holistically through all these viewpoints. What I want to talk about today is kind of look at the issue of algorithms. And in particular, because I think that's, the most surprising, I think it's fair to say that there really haven't been a whole lot of algorithmic developments in deep learning. The workhorse in deep learning by far is stochastic gradient descent, which has been around for decades, used to be called backpropagation in the 80s and 90s. And so if you think about it a bit, perhaps the right question is not so much, why does deep learning work? Perhaps the right question is, why does deep learning not work? And I'm not being facetious when I say this because, in some sense, deep learning contradicts the basic premise of conventional learning theory, which was always that you don't overfit, so if you have a bunch of points that are, say, generated from, as we have here, maybe a third order polynomial and slightly perturbed by noise, you never want to, fit the data exactly because, we've all learned that, overfitting is not a good thing to do. And deep networks take this idea of overfitting and push it to some comic extreme because they often have orders of magnitude more parameters than data points. So it's really overfitting galore. And so you would suspect that they should not generalize, but somehow they do. And in fact, there's a lot of studies that have shown that, the larger you make the network, typically the better the network generalizes. And so this is an important question to try to understand and see what is going on. And I'll try to allude to that or some reasons for that in this talk. Okay, so I'm going to look at the supervised learning setting. And I apologize, as I put together slides, I realize I've copied slides from two different decks. And so my notation in points is a little bit different, and I'll try to draw attention to that whenever it's relevant. But we have a supervised learning setting. So we have a collection of data points. The feature vectors are d-dimensional. I'll call them X throughout. And they have labels Y. You can think of X as being inputs to the network, they're vectors, and Y as being the desired output. And we assume that, these can be related through some parametric model. Think of a deep network, for example, which maps a parameter vector or weight vector W, which is p-dimensional in this setting, p for the number of parameters. So it maps W and the input to the output or to the label. And the goal in supervised learning is basically to find this weight W, ostensibly to minimize some global loss function. And I say ostensibly because often, this is a nonlinear optimization problem, and it's not clear whether we're able to do that. And so the loss function I'll call capital L of W of the weight vector. So it's a sum over all the data points of a local loss function, which is little l. And there's more general versions of this. I don't have to make it a function of the difference between y and f, but you could. And each of the terms in this summation over all the data points, I'll call L sub I. It's the local loss function, which corresponds to a particular data point. Okay. So that's kind of the setting. As I mentioned, the workhorse of deep learning is stochastic gradient descent. It has a long history. It turns out actually gradient descent goes back to Cauchy, was invented by Cauchy in 1847. It's actually an interesting paper. Cauchy was interested in solving a system of nonlinear equations, and the way he did that is he set up, the sums of squares of each of the equations when he equated them to 0, and attempted to minimize that through gradient descent. Now, Cauchy is known as being a very rigorous mathematician. And, so at the beginning of his paper, and I'm translating from the French, he says, I'll restrict myself here to outlining the principles underlying my method with the intention to come again over the same subject in a paper to follow. Because he was not happy with the fact that he couldn't really prove whether this method was going to find the solution or converge or anything like that. And the more interesting thing is that he never came back. So this paper to follow never happened. And so it shows that even something like gradient descent is a tricky thing to analyze. Now, stochastic gradient descent differs from gradient descent in the sense that you don't go along the direction of the gradient, you go along the direction of the instantaneous gradient, which are the LIs that I had here earlier, not the entire loss function, but the one that only depends on a particular data set. So strictly speaking, you're not going in the direction of the gradient. And so you can avoid local minima. There's all kinds of things that make SGD different from gradient descent. And it's been rediscovered multiple times. The earliest reference to it that I could find is due to Robbins-Monroe, but Rosenblatt, Widrow-Hoff, all rediscovered it in different contexts. The first one to use it in the context of multi-layer networks was Paul Werbusch in 1973. So what is it that SGD does? As I said, it's not really gradient descent. And so locally, if you look at every time step, it performs an optimization. So basically, you're sitting at time I, you have an estimate of your parameter vector W. And what you do is you minimize over W, the squared distance to your previous estimate, plus the inner product of W with the direction of the gradient of the instantaneous loss, if you will, with a suitable, parameter lambda, eta here, which is positive, which weighs these two terms. If you simply take derivatives set to 0, you will get the SGD update here. So this is kind of what it does locally. Doesn't give a whole lot of insight into what the algorithm is doing globally. It turns out for a linear model, so not the general F that I looked at, but for a linear model where the input output is related basically through the inner product of the input vector and the parameter vector, ostensibly plus some noise, because maybe the measurements or the output cannot perfectly be described by this linear relationship. It turns out that you can globally identify what it is that SGD does. And so this is work I did, I guess, over 20 years ago as part of my PhD thesis when I was trying to study things like H-infinity control. There is this particular law that holds globally for every iteration and across the entire trajectory of the algorithm. So if you look at, let's say W is the true weight vector, or any weight vector for that matter. If you look at the squared error between the initialization of the algorithm plus the square errors of all these noise terms, then it's equal to what you have here. So after m steps of the algorithm, this is the error in the 2 norm relative to W. And then there's 2 other terms, both of which are quadratic. The first is the difference between the uncorrupted output at time I and what you predict the output would be based on previous measurements. And the second term is similar, except that the uncorrupted output is replaced by the actual output. So there's some of these 2 square terms. The second term is sometimes called innovations. The first term is sometimes called the prediction error. And it turns out, this is it's not a very well-known property, but you can use it to prove various properties of SGD. And I just want to demonstrate that because it'll be insightful for what we want to do later. So let me assume we are in this linear model setting. And again, here's where I've switched notation. So capital N, little n here means the number of parameters. T means the number of training data points, T for training. And so I'm going to assume I'm in this interpolating regime, meaning that I have way more parameters than data points. And the reason why I'm studying this is because this is what we will study in deep learning. In deep learning, we have many, many more parameters than training samples. And because we can interpolate the data, there is no noise. There is a W that perfectly would give you the desired outputs. This is a system of linear equations, and if the xi's are, say, sufficiently, if they're linearly independent or whatever, this will always have some equation because it's under parametrized, some solution. In particular, in this setting, when there is no V, the prediction error, which is this, and the innovations are the same thing. And because there is no V, if you look at this formula I had here, this term drops. These 2 terms are the same, so they coalesce. And you get this equation. It holds for any time m that you're running the algorithm. And so if you look at this thing, the left-hand side is, of course, bounded. The right-hand side, as you let m go to infinity, has to be bounded. And everything here is positive if this eta, which is the learning rate, is small enough. So the 2 minus this thing is always positive. Under that condition, for a small enough learning rate, what this says is this EI has to go to 0. Otherwise, as m goes to infinity, this can't be something finite. And EI going to 0, if you look at it, what it means, because we're cycling through the data here, it means that you interpolate. At some point, your solution will perfectly match the data. And so what this means, and I'm glossing over details, is that you can use this relationship to essentially prove that you have convergence. So you converge to some W infinity, and this W infinity is in this set script W, which interpolates the data. So you can use that expression in 2 lines, basically to establish convergence of this algorithm when you have a fixed step size. So even though you have a fixed step size, the algorithm will converge to something, to a solution W that interpolates the data. Now, the question is, can we say more about what we converge to? And so again, if you look at the relationship I showed you earlier, and you kind of let m go to infinity, okay, so this will become W infinity, this sum will go to infinity. EI, of course, is nothing but y minus this thing here. If you look at it closely, at this identity, you'll note that the second term on the right is actually independent of W, of the true weight vector, whatever it was that was interpolating. because it only depends on y, the observations, it depends on the xi's, and it depends on the estimates, which are a function only of w naught and against the earlier i's and the earlier x's. It does not depend on the true w. W only shows up in this first term. And so clearly, if we minimize the left-hand side over all w that interpolate the data, that's equivalent to minimizing the first term, because this is independent of w. And clearly, what minimizes this first term is just w equal to w infinity, because you can make this first term equal to 0. And so what that says is that the argmin of this optimization is what we converged. It's w infinity. And so the picture is this, that so essentially what SGD does is that you start off with, your initial estimate, w naught, and as you run the algorithm, it converges to the closest point in Euclidean distance to this affine subspace, script w, which is the set of weight vectors that perfectly interpolate the data. Okay, so SGD doesn't converge to any old solution. It converges to the one closest to what you began with. So that's what I just said. And in particular, if you initialize with the zero weight vector, or excuse the zero parameter vector, then your W infinity will basically be the minimum two norm solution. So SGD essentially does a pseudo inverse for you. Okay, so this is an interesting property. It's called implicit or self-regularization. So the solution that we obtain is regularized in two norm, even though that was not the intent when people sat around to do SGD. I don't think their intent was to do this, which is why it's called implicit. Okay, and there's various other authors who've also noticed this phenomenon. And so the next question I want to ask is, what if you care about another regularizer? What if rather than the two norm of the weights, I wanted to solve this linear system of equation, or in this linear model to interpolate the data, but to use another regularizer? And that takes me to stochastic mirror descent, which goes back to, it's a stochastic version of something called mirror descent, which goes back to Nemirovsky and Yudin in 1983. And so their starting point is they start with a differentiable, strictly convex function psi, differentiable because we're going to take gradients, strictly convex because I will want the gradient to be an invertible mapping. So that's why I need both of these. This is called a potential. And so the stochastic mirror descent updates, and SMD was, I think, introduced in the early 2000s as a stochastic version of mirror descent. It looks exactly like SGD, except that rather than update the weight vector, what you do is you update the gradient of the potential evaluated at the weight vector. And so it's called mirror descent because you think of this gradient as a transformation, and this is viewed as a mirror domain which you're transforming to, and so the updates are done there. There were reasons why Nemirovsky and Yudin did this. They wanted to bring out, or to exploit perhaps any geometrical structure that might have been in the problem. It's also clear that if you take the potential as half the Euclidean distance square, you get SGD. So SGD corresponds to this particular potential because its gradient is essentially W itself, and basically that's what you get. Okay. Now, as a quick digression, because I will need this, I'm sure many of you know what Bregman divergence is. So if you have a potential function, differentiable and strictly convex, if you look at the difference between this convex function at a point W, that's what this is, and its first order approximation around a point W prime, because this function is convex, the first order approximation is always below it. And so this difference is non-negative, and it's called a divergence. And because here we are strictly convex, we'll get equality. In other words, this will be equal to 0 if and only if the two arguments in the Bregman divergence are the same. Now, when the potential is quadratic, again, most of you know this, Bregman divergence becomes squared Euclidean distance. For example, you can take any convex function you want. If you take negative entropy, you get the famous KL divergence as divergence. So Bregman divergence is a way to, if you have a strictly convex function, to create, some non-negative quantity. It's not a distance, it's not a metric, but it gives you some kind of non-negative quantity, which might be of interest. Turns out Bregman divergence shares many characteristics of quadratics, because if you think about it, if you have a strictly convex function and you subtract out the first order term, what remains are quadratics and high order terms. So it behaves like quadratics. There's a law of cosines that for, say, standard quadratics from high school. There's a Bregman divergence counterpart for that. Again, in high school, we learn about completion of squares, say when you solve quadratic equations. There is a completion of squares counterpart with Bregman divergence, which is what I've written here. The reason why I'm pointing these things out is because many properties that you have with quadratics actually generalize to Bregman divergence. And so a lot of proofs that you have that might rely on completion of squares or some kind of dynamic programming can be extended when you have Bregman divergence, okay? And so that actually turns out to be the case. So if you look at the stochastic mirror descent algorithm, there's a local interpretation of it, where now the updates, if you recall in SGD, the first term that we had was 1/2 of the Euclidean distance. In SMD, it's replaced essentially by Bregman divergence of the potential that's defining the SMD. The second term is the same. It turns out that there is also a global identity as well, the counterpart of the quadratic identity that we saw for SGD. So the first term on the left-hand side is the Bregman divergence between W and W naught. The next term is the weighted sum of the losses. This used to be the I square. On the right-hand side, we have the Bregman divergence between W and the estimate of SMD after M steps. And we have two terms that are essentially the counterpart of the innovations and the prediction errors, which involve certain Bregman divergences, which I won't go into. Now, before I say a few words about what SMD does, what I want to emphasize here is that, in conventional neural networks where, so I'm talking about the 80s and 90s, typically the scenario was, because people didn't want to overfit, the scenario was that you had more data points than parameters in the network. And so, if you're running SGD or gradient descent or any such thing, you can get stuck in local minima. There's all kinds of bad things that happen. And so finding the global optimum or the global minimum was kind of akin to finding a needle in a haystack. In deep learning, it's kind of the other way around. There are infinitely many weight vectors that interpolate the data because you are highly, highly over-parametrized. So it's as if you have, infinitely many needles, and so it might be easy to find the needles. You have needles galore, and the question is, is the needle you're finding any good, or does it have any particular property? Okay, so that's a picture I want to keep in mind. And so with that picture in mind, let's again look at what SMD does, and I'm going to do this again in the linear case and then build on it for deep learning. So again, I'm going to assume that there are way more weights or more weights the number of data points. So there are weight vectors that perfectly interpolate the data. And again, they define an affine subspace script W. Now, when you set V equal to 0 in this identity that I showed you earlier, again, I don't expect you to remember these things, but one term, the loss function of V's kind of vanish. And you get, two terms here. Again, the details are not that important. D is the Bregman divergence of the loss, the instantaneous loss. E here has a Bregman divergence term and a loss term in it, doesn't matter. But the point is, if you let M go to infinity, all three terms here again are non-negative. And so when M goes to infinity, because the left-hand side is finite, these DLI and EI terms have to go to 0. So for example, if the EI term has to go to 0, it's the sum of two terms, both of which are non-negative. So this Bregman divergence term has to go to 0, which means the arguments have to match. which means convergence, to something called W infinity. And this loss function guy has to go to 0, which means that the loss function at W infinity for every I should go to 0 if you're cycling through the data, which means that what you converge to actually interpolates the data. Okay, so this is the counterpart of the argument I gave for SGD. So SMD in this over-parametrized linear model will converge to something that interpolates the data. The question is, what does it converge to? And again, you know, it turns out, and I won't go through the details here, but if you analyze what these terms are, this term does not depend on W. It only depends on W naught in the data. This potentially can depend on W, but when you spell out what it is, you'll notice that it doesn't. Because the only dependence on W is through Li of W, and that's 0, goes away, and there's an Xi transpose W here, which is Yi, which depends only on the data. Okay, and so if you look at the identity that we have, again, we have terms here that are independent of W's that interpolate the data. And so if you minimize this first term over all weight vectors that interpolate the data, so the Bregman divergence between W and what you initialized with, the answer is W infinity, because that's clearly what minimizes this when W is equal to W infinity. So that's what we converge to.
It's the 5-minute warning.
Oh, this is the 5-minute warning? Oh my goodness, okay. Thank you, I thought okay, so then I will have to rush through this quite a bit. I apologize for that. Okay, so this is the counterpart of this implicit regularization. So what SMD does is it actually converges to what minimizes the Bregman divergence. And if you initialize W naught to whatever was minimizing the potential, it turns out that you can get a minimum potential solution. Okay, so if initialized appropriately, you get to a solution that interpolates the data but minimizes the potential. So you can choose any potential you want. The corresponding SMD will have that implicit regularization. Okay, so that's important to know, and this is just a summary of what I just showed. The picture is identical to what we had earlier, except now Euclidean distance is replaced by Bregman divergence. Okay. Now, for nonlinear models, which is what comes up in deep learning, things are more tricky. I don't have time to go through the details. And so it turns out that if you start off with a W naught, you can still show, if you start off close enough. So right now, in the nonlinear case, there's some nonlinear set, if you will, that interpolates the data. It's a manifold in certain cases. And if W star is the closest point from W naught to the manifold, this is what you would like to converge to. It turns out if W naught is close enough, that you will converge to the manifold. So you will interpolate the data, but you won't converge to W star, but you'll converge to something that's close to it. So if you started off with an epsilon distance of W star, you will end up little o epsilon distance of W star at the end. So W infinity is an order of magnitude, if you will, closer than where you began with. So this is approximate implicit regularization. And you might say this is not such a great result because this is a local result. You have to be close enough. But it turns out that this is where the blessing of dimensionality comes in. Essentially, it makes everything local, because if you are highly over-parametrized, and again, I've switched notation here, so P is now the number of parameters, N is the number of data points. It can be shown, and I can talk about this in the Q&A, that if you randomly choose a W naught, its distance to this manifold, the reason being that when you're highly over-parametrized, if you say have 10 million weights and only 10,000 data points, this set that interpolates the data is 999,990,000 dimensional. And so any point you choose with high probability will be close to a point that interpolates the data. So this assumption kind of holds by fiat. And this is really why whenever you run SMD or SGD in deep network, you typically converge to some solution a global optimum that interpolates the data. That almost always happens. And so, you know, we've done lots of simulations on data sets. This is the CFAR10 data set. It's images, 60,000 images, 10 different categories. And we took a standard network called ResNet 18, which is 11 million weights. The 60,000 data points, we use 50,000 for training, 10,000 for test. And we kind of verified within what we could do, because you can't check for every date, you know, every point on the manifold that interpolates the data, that, you know, whenever we converge, we would converge, you know, so we found a whole bunch of points that interpolate the data, and we would verify that, whenever we would start off with something and, you know, use a certain SMD, it would converge to a point that interpolates the data and is closer in the corresponding Bregman divergence to the initialization than all the other interpolating points that we had. So we verified things like this. We also looked at, you know, the distribution of the weights, you know, so we did CFAR10 with 4 different regularizers, L2, which is SGD. We did L1, actually L1 plus epsilon, because L1 is not strictly convex, L3 and L10, L10 as a surrogate for L infinity. So I can't show you 11 million weights, but I can show you the histogram of the weights that you converge to after you run SMD. So this is for L1, this is L2, this is L3, this is L10. L1 encourages sparsity, so there's more weights here at 0. There's 300,000 of them. This one has 160, so it's twice as sparse as, say, what you get from SGD. The distribution of weights in SGD looks Gaussian, and one can actually prove that they should be Gaussian. L3 kind of had the weights move away from the origin, and L10, you know, they've moved away quite a ways, you know, so they're all kind of distributed somewhere in between, because you penalize large weights as well. So clearly these algorithms, you know, the weights, they're all interpolating the data, all 4 sets of these, but they look very different. And so the question is, do they behave differently? Do they generalize differently? Turns out that they do. And we had expected when we were running these tests that, you know, we thought because of all the stuff on sparsity and Occam's razor and whatever, that the L1 regularized SMD would generalize the best. So here I'm showing you the test accuracy. Turns out that the one that generalizes the best is the L10 norm one. So this set of weights, as I said, all 4 interpolate the data, but this one generalizes the best. And in fact, on ResNet 18, to the best of our knowledge, this is the world record, you know, 94.5%. So we did 8 different runs, so that's why there's different points. And you see, you know, the 8 different runs of L10 are, you know, invariably better than what we get with SGD, L3, and the L1 is invariably worse. So this is an interesting thing. It says that actually choice of this regularizer has an effect on the generalization performance. So I know I'm short on time. I want to say a few words about explicit regularization. So if you want to do explicit regularization, you may take, you know, your loss function and add to it this regularizer, which has to be a Bregman divergence for the theory I'm about to talk about to make sense. And you in particular may want to do this if you don't trust your data. So maybe you don't want to interpolate the data and want to make sure that, you know, regularization is done as well, okay? So there's various ways you could attempt to do this. You can try to do stochastic gradient descent on this. There's no guarantee that it will converge or anything like that. Or you could use, basically, you could view, you know, this quantity here as a potential. And so this is one way you could do it. I could take, you know, this and this, you know, each of these I can assume is a zi squared. So I can take zi to be the square root of L. This is my interpolating condition. This is the potential. My Bregman divergence is this. And so I can apply SMD to this. And so what that will do, it will interpolate the data so that I get the right cost. And it'll minimize it because SMD, among everything that interpolates this data, will minimize the potential. And if you do that, you get this update. I won't go through the details. And you can prove certain convergence properties for this. So if you initialize with something that's close enough, with an epsilon, say, of the optimal for this component, you will converge to something that's little o of epsilon away. Again, I won't go through the details. I'm short on time. I'll just show you some results, which I think are quite remarkable. So we took the CFAR 10 data set and we flipped 22.5% of the, if you will, the label. So if it was an image of a cat, we said it's a dog or whatever. And then we used standard SGD. We used what we call this regularizer SMD, which does this. And we also applied SGD to that cost, so the explicit SGD. So SGD interpolates the data, meaning it interpolates the noise as well. And so the test accuracy drops, it's about 80%. This regularizer guy that we do does not interpolate the data, because what it's doing is it's actually minimizing this regularized cost, or this one, if you will. But it has significantly better test accuracy. The highest we have is 86.5%. If you do explicit SGD, so just run stochastic gradient descent on the regularized cost, there's no guarantee of convergence or where you'll end up with, no matter what we did with different, parameters, lambda and so on, it always ends up kind of interpolating the data and behaving poorly. And so I think this is an interesting thing, because we have an algorithm that provably does explicit regularization and it certainly increases the performance. I know I'm way over time, so I just have one last slide. I want to emphasize the blessing of dimensionality, which was important in deep network because everything becomes local. Zero loss solutions or interpolating solutions are easy to find. Again, this is kind of happen chance, I think, that people were using SGD and SGD had these nice properties of implicit regularization, which is really why I think they generalize well. As I mentioned, we have a new algorithm that can explicitly regularize. And I think the burning questions really are, for example, on CFAR 10, why was L10 the best regularizer? In general, what is a good regularizer? And what is a generalization theory for deep learning? So I think I will stop here, and I apologize for going over time, but I'd be happy to take any questions. Thank you.